Have you ever considered that the strongest walls aren't always, made of bricks, and the most secure locks aren't always visible?
Hmm.
In the digital world, true protection, it really begins long before a single line of code is written or a server is deployed. It's all about the blueprint.
Right, the unseen architecture.
Exactly, the architecture that defined our digital fortresses. Welcome to SecOps, the podcast created by Ben, Moise, and Sneh, and powered by CyberViewpoint. And welcome back to the series where we dive deep into the world of cybersecurity, breaking down complex topics into, clear and practical insights. Today, we're embarking on a mission critical to understanding modern cybersecurity. We're doing an in-depth exploration of security architecture and engineering.
That's right.
Our goal, to arm you with the knowledge of how secure systems are truly designed, built, and defended from the ground up.
Yeah, our deep dive today is really about getting to grips with the foundational elements of security. We'll unpack the core principles that guide secure design, explore how trust and integrity are enforced, delve into the world of cryptography, and also pinpoint vulnerabilities across the diverse landscape of modern systems, from the cloud right down to the devices in your home. It's all about being proactive, not just reactive, in building a resilient digital world.
Okay, so if we're laying the groundwork, what are the absolute non-negotiables? How do we make sure security isn't just like an add-on, but woven into the very fabric from the start?
Well, it all really begins with threat modeling. It's a systematic process to identify likely threats, vulnerabilities, and importantly, countermeasures during the design phase.
Okay.
Think of it like a really meticulous architect trying to find every single weak point in a building before construction even starts.
So you're anticipating attacks, not just waiting for them.
Exactly. We don't just wait, we anticipate.
That proactive mindset sounds crucial. So how do we even begin to identify those potential weak spots?
Well, a fantastic mental checklist for basic threat categories is the STRIDE mnemonic. It was developed by Microsoft.
Tried.
Yes, spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. It's a simple but honestly pretty powerful way to categorize the kinds of attacks we need to defend against.
Okay, STRIDE. Got it. So once we've identified potential threats using something like STRIDE, how do we start building those defenses? What are the core principles for a robust security architecture?
A really fundamental concept is least privilege.
Ah, yes, least privilege.
It just means giving users and systems only the absolute minimum access they need to perform their specific tasks. Imagine giving someone a key to just the one room they need instead of a master key to the whole house.
Right.
It significantly minimizes the potential damage if an account ever gets compromised.
That makes total sense. Less access equals less risk. But what happens if one defense fails? Is it about building, like, one super strong wall? Or is it more layered?
That's exactly where defense in depth comes into play.
Okay.
Think of that medieval castle analogy, right? You've got moats, drawbridges, outer walls, inner walls, guards at every gate.
Multiple layers.
Multiple dissimilar security mechanisms. So if one layer is breached, another one is hopefully there to catch it. It provides redundancy and resilience.
And it's not just about what you build, but also how it behaves when things go wrong, right? What about things like secure defaults and fail securely?
Oh, absolutely vital. Systems should be shipped and deployed securely right out of the box. You shouldn't have to rely on the user to manually secure them. And, crucially, if a system or a control fails, it must fail into a secure state. It should block access rather than inadvertently opening things up. You really don't want a system crashing and suddenly leaving sensitive data exposed because of some, weak default setting.
Okay, so we've got these core principles. How do organizations actually formalize them? How do we evaluate if a system truly lives up to its security promises?
Right. This is where security models come in. They provide a structured way to enforce policies. For instance, to ensure confidentiality, keeping secrets safe, we often refer to the Bell-LaPadula model.
Oh, LaPadula. Okay, I've heard of that one.
Yeah, it was developed for the U.S. Department of Defense. Its core idea is about preventing classified information from flowing downwards to people without the right clearance. Its simple security property basically means no read-up. A subject can't read information at a higher sensitivity level.
Right.
And its star property, or property, means no write down a subject can't write information to a lower sensitivity level. This helps prevent accidental leaks.
So it's not just about what you can't access, but also stopping you from affecting things at lower levels. That seems like a really powerful way to control information flow. And how do we gain confidence that these complex systems actually work as intended?
Yeah, good question. To build that confidence, we use evaluation models. A big one is the Common Criteria, which is also known as ISO IEC 15408.
Common criteria.
It's a globally recognized standard. It lets us specify what security features a product should have. Those are called protection profiles. And then it specifies how well those features should be implemented. Those are the security targets. It's kind of like a universal checklist and testing method for product security.
And underneath all of this, right at the very core of a secure system, you mentioned the Trusted Computing Base, the TCB. Can you unpack that a bit? Why is it so fundamental?
Sure. The TCB is basically the sum total of all the hardware, software, and firmware that enforces the system's security policy. It's everything that absolutely must be trusted for the system to operate securely. You have to be able to rely on it.
Okay.
And within that TCB, you'll find the security kernel. Think of it as the innermost ring of protection. It mediates all access and functions, acting as the ultimate gatekeeper. And it's where the reference monitor concept lives, enforcing those crucial access controls on data and devices.
All right, let's shift gears a bit. Let's talk about the unsung hero of cybersecurity, cryptography. That mathematical magic, right? It's not just for spies anymore.
Definitely not. Cryptography primarily ensures three main things: confidentiality, keeping secrets secret; integrity, making sure data hasn't been tampered with; and authentication, verifying identities.
Okay, confidentiality, integrity, authentication, CIA, but not that CIA.
Right, different CIA. And what's fascinating here is cryptography doesn't ensure availability.
Good point.
Yeah, if you encrypt a file and then, oops, delete the key or the file itself, crypto won't magically bring it back for you.
Right, availability is a whole different problem. So when we send sensitive information, there are different ways to kind of seal the message as it travels. Can you walk us through the main encryption methods?
Sure. When a message goes across a network, we can use end-to-end encryption. That means it's encrypted at the source, say on your phone, and only decrypted at the final destination, like your friend's phone.
Like a sealed letter only the recipient can open.
Exactly. Or we can use link encryption. Here, the message is encrypted and decrypted at every single network node it passes through. Then it's re-encrypted for the next hop.
So intermediate points can see the plaintext with link encryption.
Potentially, yes. That's why end-to-end generally offers stronger security for the message content itself, because those intermediate nodes never see the plaintext. Link encryption protects the data on each link, but not necessarily from compromised nodes along the path.
Okay, that distinction is important. And for the actual scrambling of the data, the ciphers themselves, what are the main types?
Broadly speaking, ciphers are the cryptographic transformations. We have block ciphers, which operate on fixed-size chunks of data, typically 128 bits these days.
Like processing data in chunks.
Right. And then we have stream ciphers, which encrypt data 1 bit or maybe 1 byte at a time. They process it more continuously.
Like that famous one-time pad. Is that a stream cipher?
The one-time pad, if used perfectly, is a theoretically unbreakable stream cipher. Yes, it's a classic example.
Okay, so block and stream ciphers. And at the heart of all this encryption are the keys. Managing something so critical must be complex. How do we handle the whole life of a key?
You're right. The cryptographic lifecycle is absolutely crucial. It's not just about creating a key. It involves several stages. Key generation, making strong, random keys. Then installation, getting them securely onto systems. Then use, storage, keeping them safe when not in use. Change or rotation, this is vital, ensuring keys are refreshed regularly. Then control, managing who or what can access them. And finally, mitigation, dealing with any identified defects or compromises.
So it raises questions like, are your keys being rotated often enough? Are they stored securely?
Exactly, because a weak link anywhere in that key management chain is a weak link in your entire cryptographic defense. It undermines everything else.
Okay, that's critical. Now let's dive into the core methods. Symmetric versus asymmetric keys. What's the difference?
Right. With symmetric key cryptography, you use the exact same secret key for both encryption and decryption. Think of it like a shared password or a single key for a lockbox.
Got it. Same key locks and unlocks.
Precisely. And it's incredibly fast, which is a big advantage. The Advanced Encryption Standard, or AES, is the modern standard. It's what the U.S. government uses even for top-secret data. It uses key lengths of 128, 192, or even 256 bits, making it extremely strong.
Okay, AES is symmetric, fast, strong. And then there's the other kind, asymmetric key cryptography. This is the one with two keys, right? a public and a private one.
That's the one. Two keys, mathematically linked, but totally distinct. You have a public key you can share with anyone, and a private key you keep absolutely secret.
Sounds, well, asymmetric. How does that work in practice?
It's really clever. This public-private key pair enables two fundamental functions. First, for secure messages, ensuring confidentiality. If I want to send you a secret message, I encrypt it using your public key.
My public key, which everyone has.
Exactly. But only your private key can decrypt it. So even I, the sender, can't decrypt the message once I've encrypted it with your public key.
Wow, okay. That guarantees only the intended recipient can read it. What's the second function?
The second is for signed messages. This gives us authenticity and non-repudiation, proving who sent it and that they can't deny sending it. Here, I take a hash of the message, like a fingerprint, and encrypt that hash using my private key.
Your private key this time.
Right. Anyone can then use my public key to decrypt that hash. If it matches the hash of the message they received, they know two things. It definitely came from me, since only I have my private key, and the message hasn't been altered.
So they can't deny sending it. That's the non-repudiation part.
Precisely. It's how we establish trust and verify identity online. RSA is a very common algorithm used for asymmetric encryption and digital signatures.
Okay, so asymmetric is great for secure messaging and digital signatures, proving identity. And you mentioned hashing there, those digital fingerprints for integrity.
Exactly. Hashing uses a one-way mathematical function. You put data in, and you get a unique, fixed-size message digest or fingerprint out. If even one tiny bit of the original data changes, the resulting hash will change completely. That immediately signals tampering.
So if you download a software file, you can check its hash against the one the vendor published.
Right. If they don't match, the file's been messed with or corrupted, don't run it. And what's interesting here, algorithms like MD5, which used to be popular, are now considered cryptographically broken.
Broken? How so?
Because researchers found ways to create collisions, different inputs that produce the same hash output. That undermines the integrity guarantee. That's why we now rely on stronger algorithms from the SHA family, like SHA 256 or SHA 512. They're much more resistant to collisions.
Okay, makes sense. Use SHA, not MD5. Now, we've covered principles, models, crypto, but our digital world runs on such a dizzying array of systems. What are the unique weak spots in different types of systems, and how do we protect them?
Yeah, that's a huge area. Every system type has its own unique attack surface. We need to assess vulnerabilities everywhere. Take traditional client and server-based systems. Common culprits are often things like missing security patches, basic hygiene. Also, weak encryption for communications between them, or sometimes weak or even non-existent authentication. The fundamentals still matter immensely.
And as everyone moves to the cloud, or seems to be, how does the security picture change there?
With cloud-based systems, we really have to hammer home the shared responsibility model.
Right, you mentioned that before. It's not all on the provider.
Absolutely not. It's a common misconception that the cloud provider handles all the security. For example, if you're using infrastructure as a service IaaS where you rent virtual servers, you, the customer, are still responsible for securing your operating systems, your applications, your network configuration, patching those systems.
So you own a big chunk of the security stack.
You do. The line of responsibility shifts depending on the model, SaaS, PaaS, IaaS, and it's absolutely critical you understand where your duties begin and end. Don't assume the provider does it all.
Okay. What about the absolute explosion of Internet of Things, or IoT devices? Smart thermostats, cameras, even toasters now. They seem to be everywhere.
Oh, IoT. That's a massive and frankly often terrifying attack surface.
Why terrifying?
Well, many of these devices use hard-coded default credentials, usernames and passwords that are the same for every device and can't be changed. Plus, many can't be easily patched with security updates, even if vulnerabilities are found.
Right. Remember that Mirai botnet attack back in 2016?
Exactly. That wasn't some super sophisticated zero-day exploit. It was millions of insecure webcams and home routers just sitting ducks because their owners never changed the default admin passwords, or couldn't.
A stark lesson.
It really is. It shows why these often overlooked cheap devices create such a massive collective risk.
Okay, IoT is a big one. And sometimes the biggest threat isn't a hacker miles away, but someone just trying to walk through your front door, right? How does security architecture extend into the physical world?
Physical security is absolutely foundational. You can have the best digital defenses, but someone can just walk in and grab a server.
Game over.
Pretty much. It starts right from site selection. You need to consider things like natural disasters, floods, earthquakes, local crime rates, even how close emergency services are. Then the architectural design itself can help. Concepts like natural surveillance, putting windows overlooking parking lots, using good lighting to eliminate shadows, these things naturally deter threats.
That make it harder to hide or sneak around.
Exactly. And natural access control. Using things like fences, ballers to stop vehicles, man traps, those little two-door security vestibules, or even just double sets of locked doors to prevent tailgating. It's about making unauthorized access inherently difficult.
And what about protecting the real heart of IT infrastructure, the data center and server rooms themselves?
Yeah, that requires really stringent physical controls. You're talking guards, key card access systems, often combined with biometrics or PNs, detailed asset check-in and check-out logs so you know exactly what hardware is coming and going. And, of course, continuous video surveillance.
And beyond just access control.
Environmental controls are vital, too. Proper HVAC systems to maintain the right temperature and humidity for sensitive equipment. And sophisticated fire suppression systems. Have you ever wondered why data centers often use inert gas systems, like nitrogen or argon, instead of water sprinklers?
I assume water and electronics don't mix well.
Precisely. Water can cause huge damage. Inert gas systems work by removing the oxygen from the room, starving the fire without harming the equipment. Those CO2 systems need careful handling as they can be lethal in staffed areas. And finally, power redundancy is absolutely critical. Dedicated power feeds, emergency power-off switches, big backup generators, and uninterruptible power supplies, or UPS, to handle brief outages or fluctuations.
Wow, okay. This deep dive has really shown that security isn't just about the software you buy or the firewall rules you set. It's about how you build, how you design, and how you continuously manage the entire environment, physical and digital. So, thinking about our listeners, what are some key actionable takeaways they can apply in security architecture rules?
Okay, number one, embrace shift left. Seriously. Integrate security thinking from the absolute earliest stages of any engineering process, from inception, requirements gathering, through design, implementation, testing, and into operations. Don't let security be an afterthought tacked on at the end.
Get it in early. Makes sense. What else?
Second, know your terrain. You absolutely have to understand the unique vulnerabilities of every system type you deal with: cloud, IoT, microservices, mobile virtualized systems, you name it. Tailor your controls specifically for those environments. Don't use a one-size-fits-all approach.
Right, context matters.
Third, master the fundamentals. Seriously, things like robust patch management, strong multi-factor authentication, and especially diligent cryptographic key management, rotating keys, protecting them. These are non-negotiable basics. Get them right.
Don't neglect the basics. Good reminder. And lastly,
finally, look beyond the screen. Remember that physical security, from choosing the right building location to having the right fire suppression system, is an integral foundational part of your overall security architecture. Don't forget the physical layer.
great takeaways. So from those fundamental principles like least privilege and defense in depth, through formal models like Bella Padula that help enforce policy, to the powerful tools of cryptography like AES and RSA and hashing with SHA. And finally, the critical assessment of vulnerabilities across our incredibly interconnected world, including physical security. We've really seen how security architecture shapes our digital defenses from the ground up.
It truly is the blueprint for digital safety. And maybe a final thought to leave people with. As things like quantum computing start to loom on the horizon, potentially threatening to break our current cryptographic algorithms, and as AI gets better and better at automating both attacks and defenses, what new, perhaps unbreakable cryptographic challenges do you think we'll face next? And maybe more importantly, how will our core architectural principles like zero trust, like defense in depth, need to adapt to protect us from those truly unknown future threats?
That's definitely something to mull over.
Right.
Quantum and AI, the next frontier for security architecture. Well, that's it for this deep dive into security architecture and engineering. We really hope you feel a little more well-informed, maybe more ready to tackle the complexities of building secure systems. If you enjoyed this conversation, please be sure to subscribe and tune in for future deep dives. We'll continue to unpack the most important insights in cybersecurity right here.